In this video exercise, we'll use the System Builder panel to build a model system for the streptavidin biotin complex 1-MK5 in a 0.15 molar sodium chloride solution for use in subsequent molecular dynamics simulations using Desmond. The first step is to download and prepare the protein, so let's launch the Protein Preparation Wizard panel, then type 1-MK5 and click Import. For this protein, we'll use the default settings for pre-processing, so we'll click Pre-Process. Now it looks like there are some residues with alternate positions. We'll just click OK to use the current positions displayed in the workspace. Over in Review and Modify, we'll click Analyze Workspace. We'll be using both chains A and B in our simulation, as well as both biotin ligands. Now we'll need to generate states first to ensure that they have the correct ionization state at the default pH. So it appears that this state has the lowest state penalty as calculated by EPIC. That makes sense, as we can see here that the biotin is likely to bind in the carboxylate state. So now let's go to Refine. Here we'll click Optimize in the H-bond assignment section. Optimizing the hydrogen bonding is important because X-ray structures do not usually have enough resolution to fix the orientation of terminal amides or histidines or the orientation of hydroxyls and thiols. Once that's done, we'll click Minimize. Here, a restrained minimization is performed, which removes the atom clashes and relaxes the side chains and other modifications made to the protein. Okay, now we have a prepared protein ready for the system builder. But first, let's also show the ribbons to get a representation of the secondary structure, and let's delete the labels too. Let's go to Applications, Desmond, System Builder, or if you're using the Task View mode, go to Tasks, Molecular Dynamics, System Setup, or search for the System Builder in the task tree. Now, streptavidin is not a membrane protein, so we don't need to set up a membrane here. For the solvent model, we can choose from 4 water models and 3 organic solvents. Here we'll choose tip 3P. Now, the periodic boundary conditions are set up by specifying the shape and size of the repeating unit, or box. One should choose a box shape that will best fit the protein. In this case, we'll just use the default orthorhombic. We'll ensure that buffer is selected for the box size calculation method and that all 3 distances are set to 10 angstroms. We can calculate the initial box volume here and note the volume, which is around 333,000 cubic angstroms. But by clicking Minimize, the protein is reorientated to minimize the volume of the box. So now the volume is around 303 cubic angstroms. We can also see the boundary box here. We won't use any custom charges, but we do need to set up the ions, so let's go to the Ions tab. Now here, we can exclude a region from the placement of ions and salts. Let's do that in this example. So we'll place them, say, 20 angstroms away from the 2 biotin ligands. So we'll need to click Select, then in the Residue tab, choose Residue Type, and then BTN, which corresponds to biotin. Then click Add, and OK. Now you'll notice that the 2 biotins are shown in CPK representation. For the ion placement, we'll recalculate to set the number of ions needed to neutralize the system. Here it's saying it will add 3 sodium ions. This makes sense because the status bar down below indicates the protein has a charge of -3. Now we'll click Add Salt and ensure the salt concentration is set to 0.15 molar to simulate the background salt at physiological conditions. By default, sodium chloride is added, but you can choose a variety of positive and negative ions for your salt. We'll use the default force field as OPLS 2005, and then get ready to submit the job. Now, before we click Run, we'll open the job settings, give the job a name, and then choose a non-Windows host. I'm in Windows here, so I'll submit the job to a remote Linux machine. Now just click Save and Run. System building should just take a few minutes to complete. Once the job finishes, the system is incorporated into the workspace. Here you can see the protein, solvent, and ions. We can undisplay the waters and show the ions as CPK to see that the ions are now 20 angstroms away from the biotins. The system is now ready for simulation with Desmond.